Hello all, my name is Yasin Arafat. Welcome everyone to my presentation on the paper titled A Machine Learning Approach for Protecting Wireless Networks Against Virtual Jamming Based Denial of Service DoS Attacks. Other authors of this paper are Kazi Samin Yasser, Arnab Dasgupta and Dr. A.K. Mashikur Rahman. We all agree that nowadays networking security is in wireless systems is a buzzword, as there are way more advanced attacks by hackers occurring in networking systems. At the onset, let's plunge in some ideas to get into our works smoothly. What is a DOS attack? It can be said that when an action impairs the authorized use of the services by deliberately exhausting the resources like network bandwidth in networking systems, it can be done with single or multiple sources. In this figure, a hacker makes it difficult for the other users to get the access of the server. Also, by creating virtual jamming, an attacker is able to trigger DoS attacks in wireless network. Now, what's going on here? In this wireless system, the jammer takes the channel access without sending data, deliberately letting other users not get the chance to use the channel. The depiction of figure B is the four-way handshake protocol between the sender node M and the receiver node R in the scenario of figure A. From figure C, we can evidently see that sender M is not sending the data packet at the data sending time. That makes the sender an attacker node, creating DOS attack in that scenario. Now, let's get into our main objectives. uh, Detecting the malicious nodes using machine learning based approaches, and then isolating the identified malicious nodes in order to mitigate DOS attack. Now, in order to face this problem, there exists some previous works. One is RTS validation and the other one is random RTS validation. In RTS validation, RTS packets are viewed with a restricted trust. In other words, the system senses the carrier at the starting time of the sender's data transmission and unblocks the blocked node if there happens no data transmission at that time. There are some drawbacks in this. Attackers might be concerned about the prevention mechanism, and therefore attackers can send a short dummy small sized data packet to get rid of being doubtful, resulting in creating false negative issues. Uh, Another solution is random RTS validation. The main part of this system is also the same as the previous one, but carrier sensing is done randomly. For this, sender's data transmission time is divided into some equal sized slots. Now, this is our study topology, where the green nodes are the senders and the blue nodes are the receivers and the red node is an attacker. Data transmission flows are 1 to 5, 2 to 6, 3 to 7 and 4 to 8. We run the simulation in Network Simulator 2, and figure 1 shows the throughput versus time graph where no jamming is occurred, and figure 2 is for after jamming occurs. The curve falls from 200 to 300 seconds when jamming occurs. Now, take a look at the effect of the random RTS validation. It increases the curve by some degree. Now we will see the methodology of our learning based approach. Our system runs periodically, uh, consisting of two phases in each period, and these are learning and action phases. Learning phase running for a short time is followed by an action phase running for longer than the time of learning phase. Here, learning to action ratio is a hyper tunable parameter. In the learning phase, random RTS validation is still activated along with collecting statistical data about neighboring nodes. In this period, average throughput recovery becomes 50% or so. In the latter, which is action phase, classification of all senders is done to know whether a sender is malicious or not. After that, RTS packets from malicious nodes are utterly ignored. In this phase, statistical data about neighboring nodes as different features are also collected too. Average throughput recovery in this phase becomes nearly 100%. Now, we will see the novelty of our learning-based approach. In random RTS validation, on average, half of the time cannot be recovered as about 50% resources are wasted. In our method, 50% resources of the learning phase will be wasted only. On the other hand, total resource waste percentage can be decreased by using optimized learn to action ratio. Like take LAR is 0.5, that means uh, action phase time is equal twice as much as the learning phase time. Then our approach will make an improvement of 33% over random RTS validation. Also, in question of backward compatibility, our system makes no chaos. We are following the IEEE 802.11 protocol, and there is no visible change in the four-way handshake protocol. Now we will look into our selected features for creating the dataset. Here, some technical terms are shown, like invalid RTS. That means when RTS is not followed by any data packet. And another one is IRR. That means invalid RTS ratio, which can be determined dividing invalid RTS count by total RTS count. And the selected features are moving average of IRR, deviation of moving average of IRR, and moving average of interarrival time of RTS packet. IRR is calculated in both learning phase and action phase, and we calculate the moving average from data collected from previous period, last action phase, and previous learning phase. Here are the graphs of moving average of IRR versus time for scenario with malicious node, which is figure 1, and without malicious node, which is figure 2. And the observations on moving average of IRR, the curve is high for malicious node and on the contrary low for a well-behaved node. So this feature can be helpful for classification of malicious and well-behaved nodes. Another interesting feature is deviation of moving average of IRR, which is calculated in action phase. After calculating moving average of IRR for each node, we find the average of the calculated moving average of the IRR of its neighboring nodes. Then calculate deviation for each neighbor. Here are the graphs of deviation of moving average of IRR versus time for scenario with malicious node, which is figure 1, and without malicious node, which is figure 2. See the observations on moving average of IRR. The curve is positive and high for a malicious node, and on the contrary, negative and very low positive for a well-behaved node. So this feature is also important for our classification task. And the final one is the moving average of interarrival of RTS packets. Actually, interarrival time of RTS packets is calculated continuously every time a new RTS packet is received from a specific neighbor. Now we will see two graphs. Here are the graphs of moving average of interarrival time of RTS versus time for scenario with malicious node, which is figure 1. And from figure 1 we see that the curve is very low for a malicious node. On the other hand, the figure 2 is for scenario without malicious node, and the curve for well-behaved node is pretty high than the than malicious node. So these are the significant features for our model. Now, for every learning-based task, there is a need for a dataset. But in our case, there wasn't one. So we had to create some random scenarios and collect samples from simulations run in Network Simulator 2, which is simply an event-driven simulation tool. Dataset has four attributes with a large number of samples, and there is no missing data, and some outliers are still present. Okay. Besides mentioned things, machine learning models where to feed the data selection is an important task. As the data set seems linearly separable, we use support vector machine as our model. Dataset is divided into two sets. One is 10 set, consists of 80% of the data, and the other one is test set consisting of the remaining 20% data. Uh, our SVM model learns from the training set and creates a hyperplane to classify well-behaved and malicious nodes. Now we will see the trained model's performance on test set. False positive ratio and accuracy on both train and test sets are shown here. We can evidently see that the false positive ratio is very low and the accuracies look quite good. Based on these results, we fit our learned model into Network Simulator 2 and compare our model to the previous solutions. At this moment, we see the experiment results of our work on different cases. Figure A depicts instantaneous throughput comparison between our SVM model and random RTS validation model. It is clearly visible that SVM makes the curve higher by some degree than random RTS validation does. And figure B depicts instantaneous throughput comparison between our SVM model with DoS attack and without DoS attack scenario. Our model's output curve is almost the same as the normal scenario's output curve. Now, figure C shows instantaneous throughput comparisons under different scenarios, and among all the solutions, our SVM model gives the highest throughput curve. And also the right one, which is figure D, shows instantaneous delay comparisons under different scenarios, and among all the solutions, our SVM model gives the lowest delay curve, as delay should be minimized when throughput gets maximized. So finally, to conclude, our goal is to increase the aggregate throughput more than random RTS validation by exploring significant features using a learning-based model. Another interesting fact is that if our model makes any false decision, it will fix it in the next action period after getting data from the next learning period. So, what are the what can be the feature works of our tasks? We plan to carry out our work on different aspects such as tuning LAR ratio and coefficient of IRRL, coefficient of IRR in action phase, and coefficients of interarrival time. Also, find a classification based solution for CTS only attack, where a hacker or an attacker only sends CTS packets randomly to jam the channel. Here are the references. Thank you and welcome. Now we will be taking the questions.